So we're moving on to the shortest distance from a point to a line. So the example that we have in the text talks about a ship. We've got this ship sailing out here in the ocean. A ship, which is point R, sails through point A in the direction B and continues past a port. So it's sailing here, goes through A, and it's going out this way. The ship is closest to the port when PR is perpendicular to AR. So that means that when PR is... So this line AR, if we go PR, when these lines are perpendicular, like below here, that is when they are at the shortest distance. And this actually comes from we've actually seen this as a previous geometry proof. If we're not perpendicular, realistically, the distance makes a triangle with a shorter side here. So in this sort of proof here, we've got, well, if P to point R if the dot product equals 0, which means PR is at this point here that's perpendicular to B, that means we're at the shortest point on the line. Point R is called the foot of the perpendicular from P to the line. So let's jump into an example now, and we can sort of draw this out and figure it out. A line has a vector equation, which is given here, where our initial point is 1, 2, and we're going across in the x direction 3 and down in the y direction by 1 every t. Find the shortest distance from the point to 0.5 and -1 to the line. So let's just start this off with a graph. So let's just, we'll go like so. And we'll just change colour just so we can sort of tell. Let's go black for that one. So 5 and 1 is 1. Let's go 1, 2, 3, 4, 5 and -1. So this is our point here, 5 and -1. Okay. And then we've got this value here. We start at 1, x equals 1, y equals 2. So 1 and 2, we start here. And then every time we're sort of going this way. We go 3 in the x direction, 1, 2. So 1, 2, 3, and down 1. And then across another 3, down 1. We're sort of looking like this here. All right, so that's the direction we're going in that space. 2 seconds, Indiana. Oh. All right, so we're looking at this example here. So we should be thinking, I'm just going to change to this colour. So realistically, the closest point we would sort of expect to be here. So we're going to make, I'm just estimating here, so R, which is going to be this, is going to be at a position on this line. We're looking at so we're looking at, let's just think about this. We've got this point here. Let's go R. So we've got this R point. And R has the position vector. So R has, not position, let's go coordinates. And R's coordinates are given by 1 plus 3t. So we get that from 1 plus 3t. That's our x coordinate. And then we've got 2 minus t here as well. Okay, so that gives us these coordinates. So then if we're going to look for a vector from P to R, okay, if we think about this, this was going to be OR minus OP from our previous bit. So those positions will help us in this space. So OR we've got here is going to be, now I'm going to turn this back into a vector. Okay, the coordinates can help, but we're looking at here, OR is 1 plus 3t, and then we've got 2 minus t here, and then minus OP, so this is our position vector of our point, which is 5 and -1. We're going to have 5 and -1, and this gives us our vector. So PR is going to equal 1 minus 5 is -4. So we've got -4 plus 3t. And then 2 minus t plus 1 is going to be 3 minus t. So we've got our vector all sorted now. So now we're looking for this here. So distance is minimized when P to R is perpendicular with our value here, which is B. I'm just going to use the B notation because this means now that we can write this as -4 plus 3t, 3 minus t, dot product, and we're looking at the B vector is 3 and -1, and we want this whole thing to equal 0. We want the dot product to equal 0 because that's where we get these values. So the dot product on this left-hand side is going to be 3 times -4 plus 3t, and then it's going to be plus 3 minus t times -1. And we want this to equal 0 here, which now we've got -12 plus 9t minus 3 plus t equals 0. We've got 10t equals -12, take 3 is 15, -15. We're going to add 15 to both sides to get rid of it. Equals 15. T equals 15 on 10, which equals 3 on 2. All right, so that means we're looking at that time gives us the best value here. So now we go back up to this function here, which will give us our point, okay, which if we wanted to, we can count this as the vector P. Actually, no, we don't need to do that. We're looking at PR, we're looking at this, what this vector here is, the length between them. So let's sub that in. So therefore, PR equals, what have we got there? We've got, it equals -4 plus 3, and then we've got 3 on 2 is the time, and then the other one is 3 minus 3 on 2, and this is going to equal -4 plus 9 on 2. And then we've got 3 minus 3 on 2, which is 6 on 2 minus 3 on 2. So this is going to equal -4 is going to, our top one here, -4 plus 9 on 2 is going to equal 1 on 2, because -4 is 8 on 2. So it's going to be a half. And then the other side here is going to be 3 on 2. So we can actually pull out a factor of a half. Just makes this thing a little bit easier. Half 1 on 3. Okay. Now, here it says, what does it say? Find the shortest distance. So we've found the coordinates and we've found the vector of the shortest distance, but we've actually got to find the length of this to for this to work. So can I squish this up anywhere? I'm just wondering. I'll clean this working up a bit later, maybe. Okay, so therefore, we're looking at PR, the absolute value of it, or the length, will be square root square root 1/2 squared, and then times the inside of our vector, which is 1 squared plus 3 squared, which just means a half square root, and 1 squared plus 3 squared is 10, and then it's 10 units long in that space. So the shortest distance from the point to the line is going to be given by half root 10, or root 10 on 2 equals root 10 on 2 units. And we would state that in there.